Hello and welcome to our STEAM project number 16 featuring the Raspberry Pi Pico and MicroPython. This lesson is part of our Sherpa level series designed for the somewhat experienced STEAM teacher. Today's project is the first of a short series where we build solutions in support of the Sustainable Development Goals. In this lesson, we are combining what we have learned so far in order to create an intelligent irrigation system that optimizes the use of water to grow crops and plants. My name is Peter. I am the founder of Educomondo and a certified STEM instructor. The goal of today is to develop a smart plant watering system that will only provide irrigation when needed. In other words, when the soil is dry and when it is not raining. We will see how to connect different sensors and actuators to the Pico. We will understand the logic of how the different sensors interact with each other. We will get to know some additional sensors, namely the rain sensor and the moisture sensor. But most importantly, we will make sure you and your class work as a team to find solutions, help each other, and present the project in a clear way. The idea is to build a system that measures the moisture in the soil of a plant. If the moisture drops below a predefined threshold, the water pump switches on and provides for a given period of time water to the plant. Once the soil is moist again, the pump will stop. As an additional input, a rain sensor will check whether or not there is any natural irrigation, the rain. If rain is detected, there is no need for the pump to switch on. For this project, you will need quite some items. The breadboard with a Raspberry Pi Pico, and don't forget the pinout card. A rain sensor, in this case we are using the FC37 with its controller. A moisture sensor, the TIP122 transistor, a 1000 ohm resistor, a DC motor that will work as a small pump with a plastic tube, an external power supply because of the DC motor, a 9-volt battery and the supply cable, and a whole bunch of jumper wires and Dupont cables. You will also need a small container filled with water and 2 or 3 plant pots filled with soil. Let's start building the project. First, we connect the rain sensor, the FC37. It typically consists of 2 metal contacts that are separated by a small gap. When rain falls on the sensor, the water bridges the gap between the contacts, allowing current to flow, which is interpreted by the controller and sent to the microcontroller as a 0 or a 1. Our version has a potentiometer to change the sensitivity and also has the choice between an analog or a digital output. We will use the digital output and connect it to GPIO 15. We connect the positive and the negative to the positive and the negative rail of the breadboard. Later on, we will connect the external power supply to these rails. The next sensor is the soil moisture sensor. This sensor gives us an analog signal, and we connect it to one of the ADC, standing for analog to digital conversion pins. The easiest pin is pin 26 or A0. We can connect the positive to pin 36 of 3.3 volt. The negative is connected to the ground rail. Next is the DC motor and the TIP122. The base of the TIP122 is connected to GPIO 16 via the 1000 ohm resistor. The emitter is connected to the common ground, and the collector is connected to the ground of the DC motor, and the positive lead of the motor is connected to the positive rail of the breadboard. Next, we install the power supply and make sure that the switch is off and that the 3.3 volt is selected by sliding the small connector over the 3.3 volt pin. Connect the 9 volt battery, and we're almost finished. Fill a small container with water so that the pump is submerged or half submerged. Bend the plastic tube in such a way that it will bring water to the dry soil. And now we are ready to do some live programming. Welcome to our live session. And as you can see, I have already pre-populated in the Thonny environment the most common elements that we need in terms of modules and classes. And let's start by setting up our hardware elements in our program. We have 3 pieces of hardware. We have our soil sensor, we have our rain sensor, and we also have a pump. So those are the three elements that we will need to define. So the first one is our soil sensor, and the soil sensor is going to capture an analog signal. So we are going to use the ADC, analog to digital converter, and that is located on pin number 26. The next one is the rain sensor. With the rain sensor, we are going to use a digital signal. So this is going to be on pin number 15, and it is a pin in. Right. And then we have the pump. So we will call that pump. And the pump is located to or on pin number 16, and that is a pin out. Right. The next thing we want to do is to make sure that we can capture the signals from those sensors. We have to define them and what will they be. So the first one is on the soil sensor. We are going to set up a threshold for when the soil is dry. So soil dry threshold. So that's going to be the number here that we're going to set for whether soil is dry or not. Now, in our case, I am going to set it to 45,000. 45,000 on a scale between 0 and 65,535, because we have a 16-bit architecture here. So I have seen from previous projects that the threshold in my case is 45,000. But of course you need to adjust this based on your own sensor's dry reading. Also in terms of what would be dry soil and what would be wet soil. So this is definitely a variable that you have to test and will vary and will be dependent on the situation that you are working in. The next one is the rain detection, and we are going to set that to rain detected, or we're going to call it rain detected, and I'm going to set it to 0. So the rain sensor's output will be low when rain is detected. That's the way how it will work. The next thing we want to do is also set up a debounce time, and debouncing is actually so to avoid bouncing, and bouncing is the effect that you get with sensors that they are not giving a clean signal towards the pins. This is very apparent with sensors that work with water, that work with other environmental conditions, because they capture so many data at the same time that from time to time there is a false reading or there is a bad reading. And to avoid that, we are going to introduce something which is called a debouncing. And debouncing is actually defined through a time. So we are going to set a debounce time, and we set it to half a second. What else do we need? Well, we want to give a burst of water created by the pump, and we need to set how long that burst is going to take. So how long the pump should be activated if the soil requires irrigation. Now, this is a very small pump. Nevertheless, in our lab setup, you have to be careful that the pump is not giving too much water and that everything starts to overflow. So the best way to start is to start with a very short amount of switching on the pump. Let's start with 1 second, and we will call it the max watering time, and we're going to set it to 1 second. When we are running the project, you can make adjustments. You can say we want to have 2 seconds or 3 seconds, or you can even make it shorter, because even if it is a very small pump, there is quite some water that is coming out of it. So better to be safe than sorry. I think we have created all of our variables. So let's now create a function that will control the debouncing. So definition, and we call it debounce of the rain sensor. And the way that we will construct it is that first of all, we are going to check for a state a number of times, multiple times, to avoid these false positive, to avoid these wrong readings. So we will call last state, and we will equal that to the rain sensor value. Let's say value in between rounded brackets, and we will have a for statement. We are using the simple underscore as a kind of throwaway variable. So for variable in the range of, let's say, 2, so 2 readings, so check twice with some delay, and that delay is going to be the sleep of the debounce time that we have set divided by 2, because we do twice the reading. Here we add another if statement, because if that rain sensor value, so that rain underscore sensor dot value is different from the last state, which we have just set to the last state, but if it's different from the last state, and I'm using exclamation mark and equal sign, what's going to happen? And I see that I forgot here a couple of points, as you probably have seen that this is of course not correct. So thanks for spotting it. If the rain sensor value is different from the last state, then what will we do then? Well, then it is going to return a false statement. So the sensor state has changed, and it's not a reliable reading, because we expect that the reading will continue the same and it's not going to bounce between zeros and ones. And the next thing that we do is we are going to set it once again to the last state. So last state is going to be once again the rain sensor dot value. Now to close our for loop here, we are going to, or to complete our function here, we are going to put a return. So what is the return of this function? Well, we are going to return a last state, and that last state is going to be equal to the rain underscore detected So the sensor state at that moment is consistent, and at that moment we will have a return from that function, and it will say, yes, we have detected the rain. So think a bit about this whole logic. So we are actually comparing all the time the different readings. If the readings are different, it means that it is bouncing between zeros and ones. If the readings are equal, it means that it is the same, and then it will say, only then it will say, yes, a rain is detected. Or when there is no rain, it will of course not say rain is detected, but then it will not say anything. It will only do something. It will only react when the drops of rain are hitting the rain sensor. Okay, so that's our function. It's also the only function that we will be creating in this project. And I think we are now ready for our main loop. So our while true. And our while true is first of all going to start by reading the moisture. That's of course the main parameter. So we are going to create our soil moisture value, which is the soil sensor read. So soil underscore sensor dot value. So not value, but read underscore U16, open and close the brackets. It's going to read that value from the sensor, from the soil sensor, and we are going to print a short message in our shell, in our REPL, and let's print something like soil moisture value, and that value is the soil moisture value, soil underscore moisture value. The next thing that we want to see in our feedback mechanism, in our REPL, is to read the rain sensor. With, of course, making sure that the debouncing is also checked. So we are going to have rain detected underscore detected is the debounce rain sensor, because we are going to call this function. And it's going to also here print. That's what we want to see. We want to see here rain sensor value, and that rain sensor value is just the rain detected, so the value that we just declared one line above. As I said, we need to check whether or not the rain is detected or not. So we have to have an if statement here, because if the rain is detected, we don't want the pump to switch on. That's the smart part of this program. It will only create a pulse to the pump to water the plant if the soil is dry. So if it's either below or above a certain threshold, depending on how you set it up. And it also is going to check whether there is no natural irrigation through the rain, which will of course make the soil wetter but at a lower pace, but it will do it. So that's why we are including it. So if the rain is detected, if rain detected, then what do we want to do? Well, we are going to print rain detected with an exclamation mark, and we're also going to say that it is stopping the watering, so stopping the pump. Which is a good feedback to the user so that he or she knows what is happening and where we are in the cycle. But also it's a feedback that indeed the pump is stopping without actually having to look at what the pump is doing. So even from a remote perspective, this is a good feedback. So if the rain is detected, first we are going to print the rain is detected, so stop the pump. Of course, we also need to stop the pump, so we are going to set the pump dot value to 0. So that is setting up the pump. What else? Else, if the pump is, or if when there is no rain detected, then we also have to say that only if the soil is dry. So if the soil moisture value that is being read from the sensor is larger than I'm just going to check here where my larger is. Here it is. If the soil moisture is larger than the soil dry threshold, soil dry threshold, what do we want to do? We print once again a message, and that message is soil is dry, exclamation mark, watering the plants, watering the plant or plants. We set the pump value to 1. Which is going to switch on the pump. And here we also define for how long. So the watering start is going to be time dot time. And we are going to have a while statement here. So while time dot time minus the watering start is smaller than the max watering time. And we're going to put it to sleep for maybe just a short while. Sleep for half a second or even less, a tenth of a second. And the pump value is going to be set to 0 again. Right, so that's that should control our pump and also the watering time. So the watering start time is equals to, and this is a specific way of writing it. So just use the time.time. So while that time.time minus the watering start, so during that duration, and it is shorter than the maximum watering time, then it continues and it will sleep for a tenth of a second, and then it will pump. It will put the pump value back to 0. So that's okay. This is, of course, if the soil is dry. Else, so I think we can also have an else statement here at this level. Else, we print the soil is moist, no need to water. So we check for the soil moisture value in the if statement, which is embedded within the else statement of the rain detected yes or no. Then it is going to check, it's going to start the pump. The pump is going to go on for a given period of time that we have predefined. It's checking that time, the time that is moving. As long as that time is shorter than the max watering time, it will continue. If not, then it's going to go to 0 and switches off the pump. Of course, if the soil moisture value is not dry, so it is wet enough, then what we want to print also a message by saying the soil is moist or is wet, and there is no need to water the plant. And the pump value is at that stage also 0. I think we're almost there, because the last thing that we want to end is to have another sleep. And I think we can put it here below this else statement, and we will wait for another 5 seconds to run the while true setup. Now I've taken 5 seconds. In reality, this is probably not going to be that fast, because you want to give the soil the time to actually be irrigated with water, sufficient water. So in reality, you would probably only do this maybe every 3 minutes or 4 minutes, whatever is required in your project. I think this is it. So let's give it a try and run the program. And I see here an error, so I've forgotten a couple of times the double points. So let's run it again and look for all the errors that I made. Line 21. If the rain sensor value is different from, no, this is not needed here. Line 41. And once again, I forgot here the colon. And hopefully the last one in line 42. 42, sleep. I think I have here a syntax error. Be careful with the indentations because they are quite important, as we know in MicroPython. Yeah, that should do the trick. And soil moisture value isn't defined in line 28. Of course, it's not like this. It's an equal sign. This is it. Okay, let's look at our project, and I think this was also a very good exercise how to debug. As you can see, when you are doing these live sessions, it's very easy to forget or to make small mistakes, and those mistakes can easily be corrected by following the leads given by the Thonny environment. So let's have a look at our project and see how it is going. So here we are with our setup. You can see that I have powered the breadboard. Our sensors are showing that they are alive. Very important that they have been powered sufficiently and correctly, otherwise you will have wrong readings. My moist sensor, I'm going to put it here in our plant, and as you can see, it's a plant that is hopefully in dire need of some irrigation. I'm going to put it in the soil and I'm going to start the program. It says that it's moist, so no need to water. So it is sufficiently moist, so that's too bad. So let me change the value to a different level. So instead of 45,000, I'm going to use 35,000 and run it again. And yes, you can see that it starts to run. It bursts of half a second. You can see it very nicely, very clearly. And it will gradually lower the value of the soil so that at a given moment it will stop. Now, while it is working, what I want to do is to create some rain and see if that one works. So I'm going to put some drops. And indeed it says rain detected, so stopping the pump. So that works nicely, very nice. Going to clean it. Okay, and now what I will be doing is I'm going to put it maybe here where it's a bit more moist. And it says it's moist, no need to water. So you can see that the value is in its 20,000. So it seems to be working. And that's hopefully also the case with you and in your classroom. And hopefully you will be able to make this work again. If it does not work, no panic. You know what to do, logical fault finding. And I'm pretty sure that you will be able to make it work also. Let's go back to our lesson. This project is a great starting point to talk about climate change and SDG 13. Let your students do some research on SDG 13 and what it really means. If you are in a rural area, ask your students how irrigation is happening today and whether this project could be a smarter solution to grow crops without wasting water. You can expand this project to run as a standalone, like we did with a weather station, adding a solar panel power bank, an LCD display, and use it to water some plants in the school garden or in other classrooms. Your students can present the working to other classes. You can also add additional sensors like the DHT11 to fine-tune the control of water with additional operating parameters. And that's it for lesson number 16. I am confident that you and your class found it useful and fun. In our next project, number 17, we will measure the quality of water using a turbidity sensor as part of a mini water filtering plant. I look forward to seeing you again. Bye bye for now.